Melissa's actually going to start.
Hi everyone, so I'm Melissa Mokhtari and this is my colleague Jonathan Mather. We are with a team at UC Berkeley who has worked on smart energy control using blockchains, and we're really excited to be here and share our work with you. So let's get started. In recent years, we've seen a huge emergence of renewables and distributed energy resources all around the world. By 2030, for example, the state of California aims to have 50% of its electricity consumption come from renewable sources. And they plan to do this largely by integrating distributed energy resources, or DERs, into their action plan. Germany and France, and possibly soon China, also plan to do something similar by completely phasing out gas and diesel vehicles by 2040 and going fully electric. Because of this, we can expect to see a lot more electric vehicles on the road and connected to the grid. So this all falls under the category of distributed energy resources, or DERs, which are any energy resources that need to be charged or discharged on a certain schedule. So this includes electric vehicles, smart appliances, battery storage systems, or solar panels. And they have the potential to reduce costs, improve reliability, and help integrate renewables into the energy network. However, in order to function properly, they need to be coordinated very effectively. And otherwise, this would result in system outages or costly component failures, which just do not benefit any actors in the network. So designing distribution networks to support DERs requires a trusted coordinator to manage demand without the use of large-scale generation. So right now, the central utility who handles the generation and distribution of energy, their methods are starting to become outdated as we see more and more DERs onto the network. So furthermore, people who invest in DERs would want to maintain control over their assets and not have to relay their energy scheduling information to a large central utility. This incentive to bypass a central utility in the electricity network without compromising security or reliability makes this type of network a very strong candidate for a blockchain-based solution. So, seeing this opportunity, our team has developed a way to coordinate DERs using smart contracts. And we did this by combining our unique distributed optimization algorithm with a blockchain-based platform to coordinate DERs while still maintaining within the physical constraints of the grid. And I'll get into more detail about this in a bit. Meanwhile, this eliminates the reliance on central utility companies in the network, which would solve the problem of, it would eliminate the reliance of central utilities as they are today if they, since we inherently need a degree of centralization to manage the transmission lines, but their methods will be updated to accommodate for the new resources that are being implemented. So now we're going to show you a brief video about our project before we go into more technical details about how it works and why it's special.
Smart energy control using blockchains. The emergence of controllable distributed energy resources, or DERs, creates a unique opportunity for reducing energy prices while reducing costs. But if these DERs aren't coordinated effectively, and if the network constraints are ignored, this can lead to blackouts due to high power flows from electric vehicles and solar panels. So your electric vehicle doesn't get charged, or your solar energy doesn't get used. To address this, academic researchers have developed sophisticated algorithms for scheduling energy resources to meet device constraints and to prevent blackouts by respecting network constraints. Our research team has worked on decentralized algorithms that can make these problems feasible for hundreds of thousands of devices. The goal is to be able to coordinate the flexible energy resources of an entire city in order to reduce energy costs and emissions for everybody. Take a decentralized power flow algorithm that respects network power flow constraints and combine it with an economic dispatch algorithm which minimizes the cost of procuring energy services. We've developed these algorithms to be decentralized so that they can reach the best schedule possible and trade information peer-to-peer on a decentralized network. This approach can preserve the privacy of each household, so you don't have to tell your utility when you want to use your car to be charged, your laundry to be done, or how much you want to pay for energy. We are taking advantage of blockchains not just as a secure ledger, but also as a secure computation platform. We're using smart contracts to coordinate the decentralized optimization process and to ensure that we're able to arrive at an optimal schedule that reduces costs for everyone and prevent cyber attacks. The schedule is run a day ahead or an hour ahead and can be updated to reflect new information about demand and device constraints. Once people start consuming energy, our trusted smart meter logs that against their committed schedule and automatically pays them for energy that they can provide or charges them for the energy that they consume. We are a science-driven team. At our core is research on decentralized optimization of power systems, a deep understanding of power markets and blockchain technology, and a passion for transactive energy systems. Our team is led by Eric Munsing and Jonathan Mather, who are finishing their PhDs in civil engineering and mechanical engineering respectively. We're also led by members from blockchain at Berkeley. We've developed a tabletop prototype network that works in the lab controlling small loads of energy. The Wangshan project is an incredible opportunity for us to springboard our work and jumpstart into hardware deployment and integrate more controllable energy loads into our network. We envision a future where peer-to-peer energy exchange is made seamless, effortless, and affordable for all. By pioneering the intersection of smart contracts and distributed energy resources, we can achieve an efficient energy exchange protocol which fulfills energy demand while minimizing infrastructural costs, making an effective and realistic model for the energy grid of the future.
As we've seen, DERs have the potential to provide many system benefits while minimizing costs to the users. However, as I mentioned earlier, coordination is key to being able to realize its potential in the best way. Namely, any energy system, regardless of how it's operated or how many DERs there are, requires a balancing of load and demand while maintaining in a small time period and a low cost. In addition to meeting these low cost factors, the energy system would have to ensure that the resulting power transmission doesn't exceed the limitations of the existing power lines. So we made sure that our algorithms do not exceed a voltage or current limit in the existing lines that are to be used. And this is, as far as we know, unique to our purpose when we were developing this project. Today, this problem of energy transmission with DERs is solved by central utilities who operate using a relatively small number of large generators. But with hundreds of thousands of DERs being added to the network, eventually these centralized algorithms to optimize energy transmission will become computationally intractable because there are too many variables to consider. So instead, to solve these large scheduling problems, we can use decentralized optimization algorithms, which basically means that we take this very large, complicated optimization problem and break it up into smaller, easier pieces, solve those pieces, and then somehow bring them back into consensus through peer-to-peer communication or an aggregation step. While these decentralized optimization algorithms are computationally scalable, they do require all members of the system to trust each other completely. And they also don't inherently prevent cyber attacks or prevent users' energy usage data from being given to someone else or being open to the public. This is where we see incredible potential for smart contracts in coordinating DERs to provide a consensus-based security level for these decentralized optimization algorithms. And now John is going to tell you more about how this process works step by step. Go ahead.
Brilliant, thanks, Melissa. So yeah, I want to dive into our technical approach to kill some time. I think it's interesting to go through some of the details. So imagine a distribution network. There'll be lots of homes on that network. or with their own distributed energy resources, solar panels, electric vehicles, energy storage, anywhere where you have some degree of control over the timing and consumption of that load. So each home is also going to have a set of preferences about how they want to use those loads. Firstly, around timing. Maybe I only want to charge my electric vehicle between 8 p.m. and 6 a.m. the next day. And then around cost. Maybe I only want to charge my electric vehicle if the cost of energy is below 20 cents per kilowatt. So if I wanted to coordinate all these energy resources, I could collect all these parameters and variables, put them into one big problem and try and solve it. But as Melissa's discussed, with the huge numbers of DERs on the network, this is just completely intractable and not possible. So what we want to do is split up the problem into little bits. So we have each home has a set of local variables and parameters that are unique to that home. So device constraints, their preferences. And then there are a number of global shared variables across the network. So these are shared among all homes, and these are the power flows on the network, the voltage levels. So we need a way of making sure that every little home is happy with their local optimization, but they can all agree on these shared variables and shared parameters of the entire system. So the way we developed to deal with this in our research is using these decentralized optimization algorithms. So in practice, the way this works, every home has their own optimization problem that they solve, and they have some belief about these global shared system parameters. They solve that optimization, and then they send these parameters to a simple, cheap aggregation step that lives on the blockchain. This aggregation step takes all of these beliefs about the shared variables and computes what we can think of as an average, or an average of the belief of the network. It also calculates a set of prices for the network. It takes those variables and sends them back to the homes. And then the homes recompute their optimization with this new information. And we iterate this process until we reach consensus, where every home is happy with its own optimization, and they all agree on what the state of the system should be. And if we find this consensus, we publish that to the blockchain. So this is a day-ahead or hour-ahead energy schedule. It's also auditable, so people can check that it was computed in the right way, correct. And then we have homes prepay for energy using payment channels on the blockchain. And then throughout the day, we monitor their consumption through our smart meters, and then we check any deviations from their schedule and their charge according to the prices that we calculate. So the real innovation here is taking what's an expensive computational step and taking that off the blockchain, putting that on local nodes, local devices. The step that's on the blockchain is a cheap, simple aggregation step that all participants can audit. I also wanted to take this opportunity to address some inherent centralizations of energy that you can never get away from. So blockchain is this fantastic decentralized technology, but energy doesn't quite play so nicely. So you always have to have somebody who is responsible for the wires. Someone has to own them, they have to maintain them, and manage constraints. It's difficult to do in a decentralized way. So you can never get away from that. I have to send electrons down a wire to my neighbor. Secondly, around meters. So in this scenario, it's not like sending a Bitcoin or an Amazon package. It's a continuous flow of energy throughout a day, which is metered, and I have to trust the smart meter data coming to me from each individual. So the meter becomes a point of trust in the network. It becomes an oracle for the blockchain. So how you trust this oracle data stream is a really sticky problem. It's something that we're actively researching. So why would you want to use this solution? We've calculated that we can deliver 30 to 40% savings over a conventional approach to energy management. This comes from reduced investment in capital infrastructure costs, reduced energy procurement costs from coordinating loads and DERs, reduced administrative overhead and billing, and then also, what's more interesting maybe, is reduced credit risk, repayment. We also get all these great cybersecurity benefits that blockchain brings. And more broadly, coordinating DERs and having a successful method of doing that enables far greater increased penetration of renewable energy across the grid, at large scales and small scales. is obviously incredibly important for China's energy future. In terms of differentiation, what makes us different? We care about physics. Blockchain is fantastic at economics, and lots of people like to think about economics, but when you're thinking about a physical system where there's lots of existing infrastructure, you have to consider how the actions of each individual is going to affect the flow on that network. And our approach directly and explicitly incorporates that. We also maintain privacy of local users. That's what I'm saying. Your own data, your own assets, you retain control of that. You don't have to send it to a central utility. And the end result is a trustless, decentralized calculation of a power schedule and prices. It's a really valuable and unique proposition. So in terms of our team as well, we're very much researchers first and foremost. So Eric and myself developed this research, PhD researchers at UC Berkeley. I'm very happy to hear Vincent is along there as well. And then we've also been very fortunate to work with Blockchain at Berkeley, who are a student organization who have fantastic domain experience in blockchain technology, and also extensive experience of providing consulting services to corporate partners on a multitude of projects. Finally, I wanted to talk about how we might think about monetizing this kind of platform. So a first simple approach might be through small transaction fees on each network, and then we can think about how that translates into a bigger project, say for the Innova City. So we estimate that a 100,000 home project would have capital costs of about $3 million, $2.5 million, and we're generating $750,000 of revenue each year, so maybe a 4 to 5 year payback. And this is not even counting all those additional savings that I talked about earlier that you get from using this approach. In terms of our roadmap, right now we have a desktop proof of concept, coordinating smart devices on a private Ethereum network. Our next big step is a microgrid pilot deployment project with our utility partners that we're in discussions about creating right now. And then throughout the end of 2018 and early 2019, we're going to be scaling up our development, our manufacturing, and then having a commercial product ready to go by 2019. So I want to finish by saying we're really excited and happy to be here, coming from San Francisco to Shanghai. It's a beautiful city. And we're really keen to talk to anybody who's interested in researching this, investing and funding this kind of work, or also partnering with us. If you think this kind of decentralized approach is useful for your own projects, or your microgrid, we're incredibly keen to find partners and think about how we can push this research and work forward. Thank you very much for your time.